Hello everyone. I hope everyone is doing good and well. So for this week, we'll be focusing on chapter 9, which is basically the calculations of chemical formulas. Now, this chapter is mainly composed of calculations, so I'm not gonna do two videos whereby I do theory and calculations. I'm just gonna do one video throughout, and from there I'll provide you guys later on with some PDF questions whereby we'll be running through some questions. Okay. Now, for this chapter, there are five things that you be looking into, or rather, we be calculating, and that's the calculation of moles, number of moles, empirical formula, molecular formula, and percentage composition by moles. All right. And before we go any further, please do note this point here. Note it. Note it. It's very important that you should never, ever, ever, ever round off unless you're instructed to, and make sure that you always use the period table that you're given in class. All right. Good. Now, the first one, the moles. And the moles now, that's where, for moles, the calculation of moles is going to be using our mass and our molar mass to calculate it, right? So how do we express the mass? You use the grams, okay? It is usually expressed as atomic mass unit, but we're going to express it as grams. So usually it will be, maybe example there for gold, it will be 197.0 atomic mass unit. You can express it as 197.0 grams. All right. And another thing that you need to note before we go any further is that 1 gram atomic mass of one element has the same number of atoms as 1 gram atomic mass of another element. So what this basically means is that when you get like two different elements, like sodium and sulfur in this case, they will have two different masses, right? The masses here are different, but they will have the same, in each one mole of them, they will have the same number of atoms, okay? They will have two different masses, but each mole of it, 1 mole of sulfur and 1 mole of oxygen, will have the same number of atoms, which is 6.02 10 to the power of 23, right? And that is your Avogadro's number. This is what you'll be using in class. This is what you'll be using when you calculate. All right. So for the moles, there are two questions regarding it that you will normally get or likely to get, and they will go as thus. The first one will go like, you should calculate moles, not the first one, but this is how they actually go. You should calculate the moles given in a certain mass. You were asked to calculate a mole that's given in a certain mass. Moles given a certain mass, actually. Sorry about that. You should calculate moles given a certain mass. And you should also calculate the grams for a certain number of moles. So it's just basically vice versa, if you actually analyze it. So the easiest way to do this is by using this triangle here. The easiest to tackle it faster, and you can use the other method of the cross multiplication method that Dr. Coates was illustrating in the video of session A. But I prefer this one, but you can use that one too. It's still fine. It doesn't matter which one you use as long as you get your correct answer. So this vertical line here, just simply, this vertical line here, let me just start it. This vertical line here simply means you multiply, and this horizontal line here simply means you divide. Just diversion line here, the multiplication line there. So if you want the mass, you say moles multiplied by the molar mass, and this, the molar mass, is always given in the periodic table. Okay, it's a given because it's there in your periodic table, right? So you be asked to calculate the mass or the moles, not this. They cannot ask you to calculate something that's already there. It's already given for you. It's there in the periodic table. All right. And then let's look into examples. Now, the first one reads thus: how many moles of oxygen are in 64 grams of oxygen? Right? You want the number of moles. How many moles of oxygen are in 64 grams of oxygen? So we're given the mass. this, my guy here, is always given. So therefore, we want this, right? We want this guy over there. So we know that the number of moles is the mass over the molar mass. And the mass is given to us as 64 grams, right? So we say the mass there over the molar mass. And then you write it's going to be 64 over 15.999. 15.999 is there in your periodic table. That's the number you're going to get in your periodic table. Make sure that you use what's given in the periodic table. Don't write 60, write this one. Okay, and this is the final answer that you get. If you divide, if you say 64 divided by 15.9999, you will get this number. All right. And then the second one is, what is the mass of 0.85 mole of oxygen? Here we want the mass. We want this guy on the top. And we know for the mass, you see the number of moles, multiply that by the molar mass. And again, it's always given in the periodic table. All right. So we are given the number of moles as 0.85. So you say that 0.85, you multiply that by 15.9999, it will give you an answer of 13.59915. As you can see, I write all my numbers after the decimal point. Okay, please do so too. Do not round off. Okay, good. And then you look into the number of atoms. Now with this one, that's now where you can use that cross multiplication. Not now, you can use it, but yeah, for this one you're gonna use that cross multiplication method. How many atoms are there in 0.25 moles of argon? So use the cross multiplication method. Like I said, you write the moles on one side and the atoms on one side. You can see on the other side of the equal sign, we only have the moles, and on the other side of the equal sign, we have the atoms. Okay, so we know by now that 1 mole of an element equals to 6.02 times 10 to the power of 23 atoms, right? So if that equals that, we can easily find how many atoms are there in 0.25 moles. So basically what you're going to do is you will say 0.25, you're going to times that by 6.02 times 10 to the power of 23, and that will give you the x that you're looking for here, which is 1.505 times 10 to the power of 23 atoms. Right. And now we look into the empirical formula. Now, what is an empirical formula? An empirical formula of a compound is the simplest whole number ratio of the atoms that make up a formula unit of the compound. Okay? So, the percentage by mass of each element in a compound is used to find the empirical formula of a compound. We're going to use the percentage by mass of each element to find the empirical formula. Right. Now, let's look into an example. It states here, determine the empirical formula of a compound whose composition is 29.5% of nitrogen and 74.1% of oxygen by mass. So how do we go about? First, you should determine the number of moles first. So how do we determine the number of moles? You say the mass all over the molar mass, right? Like I was saying, the mass here, it says now it says whose composition is 29.5% and 74.1% by mass. Okay, so therefore you can convert that to your grams. Okay, right. So you firstly find the number of moles of each nitrogen and oxygen. Now, we know by now that when you want the number of moles from that triangle of ours there, that the number of moles that's in here, you say the mass all over there, the molar mass right there. So we say the number of moles is going to be the mass divided by the molar mass. So therefore, the mass, like I said, you're going to convert this into grams. So it's going to be 29.5 grams divided by 14.007 then. That one of nitrogen, here it is, 14.007, and it will give you this answer. Do not round off, this one on the top, 2.106089812 moles. Okay, you don't round off yet. Okay, in the empirical form, that's where now you can round off, but you don't round off yet. Don't rush to round off. And then you do the same for oxygen. You want the number of moles, you say the mass, that's 74.1 grams. You divide that by this 15.999, and you give you 4.63153947 moles. All right, and from there you divide by the smallest number, and you can tell that the smallest one is that of nitrogen. So if you divide this number by this number, it will give you 1, right? It's obvious, it's a given fact. And then from there you say 4.063153947 divided by 2.106089812, and it will give you 2. And that will lead us to our final answer, being the empirical formula is NO2. All right. Now, before we go to the molecular formula, let's just go through the